Yes, so next let's move on to the next topic, which is sampling theorem. So what it does, so sampling theorem deals with reconstruction of the signal from its samples. Okay, so reconstruction of the signal with samples. So let us say x of t is our signal. Okay, so let us say x of t is our signal and its samples are given by xs of t. So now question is, okay, samples are given by xs of t. So now question is it possible to get back x of t from xs of t? So don't worry, we will talk about all the details soon. Okay, but what is the what does the sampling theorem deal with? Sampling theorem deals with the question like given the samples of the signal x of t, which is xs of t, can we get back the signal x of t? So this we call it as what? This we call it as sampled signal. So this we call it as what? Sampled signal. Okay, so this is the sample signal and this is our original signal x of t. So sampling theorem deals with getting back our signal x of t from xs of t. So if you look at the if you join the peak values or the Dirac delta function, so what you see, you get back your the signal x of t. So if you look at the if you join the peak values, you can see the replica of your original signal x of t. So intuitively, what do we say? Yes, it is possible to get back your signal x of t from samples of x of t. But how does that happen? That we will see mathematically. Okay, so again, I repeat here, sampling theorem deals with getting back the signal, our original signal x of t from the sample signal xs of t. But why should we study this? Why should, when the signal itself, when the signal x of t itself is there, why should we talk about samples? So if you look at the current scenario, most of the whatever we do, that everything is digital domain. So digital domain means what? Whatever we do, they are stored in memories, correct? So you have to store whatever you do inside the memory, do some processing, and then we transmit the corresponding signals or process the signal. So for example, whatever I am speaking, that is stored inside a computer. How is that done? So whatever I am speaking is what? That is analog signal. That analog signal will be converted. So we have a transducer in this microphone, and what it will do, it will transmit the signal. And what will happen inside the computer? Inside the computer we will store the samples of my speech signal. Okay, so but because we have finite memory locations, so definitely what is the requirement? We require our signal to be sampled. Why? For example, if you look at our, let's say this is my speech signal. Okay, so because it is a continuous signal, theoretically we require infinite number of memory locations to store it, but practically it is not possible. You cannot store infinite number of samples inside a computer, and hence the question is, if I store finite number of samples inside a computer like this, so let's say this tens of Dirac delta functions, if I store them in a computer, can I get back our original signal x of t? Why? Inside a computer, all the whatever we are speaking, maybe voice, maybe image, everything is stored in which domain here? It is stored in digital domain, like it may be stored in ones and zeros. But for example, if you want to listen a music, so what should you do? The signal should be given to your ear. So but ear is what? It's an analog, it can perceive only analog signal. So then what we do, we will retrieve the signal from the memory which are in ones and zeros, and then we reconstruct the signal. So whatever I am speaking, same thing you should listen. So that we call it as what? Reconstruction. So what is that we are doing? First, analog signal is converted into samples and they are stored inside a computer, and then if you reconstruct, I should get back the same signal. If now question is it possible to reconstruct from the finite number of samples? And that is dealt with which topic? Sampling theorem. Okay, so hopefully that motivates why we are studying sampling theorem. Okay.